Welcome to mixed Fourier series. So recall for the boundary value problem, with y double prime plus lambda y equals 0, with initial conditions y prime of 0, or sorry, with boundary conditions y prime of 0 equals y of L equals 0. We wound up with the eigenfunctions. Cosine of 2n minus 1 pi over 2l all times x. Again, that x is inside the cosine. So these are different from the functions we've been working with in our Fourier series. So again, these are different from the functions we've been using for Fourier series. And then we also had for the BVP y double prime plus lambda y equals 0, with boundary conditions y of 0 equals y prime of L equals 0. We had wound up with the eigenfunctions sine of 2n minus 1 pi over 2l x. Again, not the functions we've been using for Fourier series. So it turns out that we can use these functions to make series themselves. So the mixed Fourier cosine series, we refer to it as mixed because the boundary conditions are mixed. One is on y and one is on y prime. So we have our mixed Fourier cosine series, uses these cosine terms. So the mixed Fourier cosine series is f of x is equal to the sum from n equals 1 to infinity of c sub n times cosine of 2n minus 1 pi over 2l x. Again, our c sub n look basically like what we had in the case, I should say this is the mixed Fourier cosine series of f. This is our mixed Fourier cosine series of f on 0L. Is f of x is equal to the sum from n equals 1 to infinity of c sub n cosine 2n minus 1 pi over 2l x, where c sub n is 2 over L times the definite integral from 0 to L of f of x times cosine of 2n minus 1 pi over 2L x dx. So again, this looks basically the same as our cosine series. It's just that we have changed our sort of the thing multiplying x within our cosine function. It turns out that this is essentially f, or converges to f, except at the discontinuities and boundary. So once again, this converges to f, except at the discontinuities and the boundaries. Similarly, we have a mixed Fourier sine series of f on 0L. And this is simply f of x is equal to the sum from n equals 1 to infinity of d sub n sine of 2n minus 1 pi over 2L x. And our d sub n, again, is equal to 2 over L times the definite integral from 0 to L of f of x times sine of 2n minus 1 pi over 2L x dx. Once again, this converges to f, our original function f, except at the discontinuities and the boundaries. Solving for our d sub n is essentially the same as solving for the b sub n we had before, just with a slightly modified coefficient in front of our x within the sine function. So depending on the context we're in, sometimes we're finding just a standard Fourier series, sometimes we need to find a cosine or sine series, and sometimes we need to find a mixed cosine or mixed sine series. So we will use the various different types of Fourier series when solving partial differential equations with boundary conditions. So these are just a couple additional series to keep in mind. The one we use is going to depend on which particular boundary value problem we are working with.